Good morning. I'm Katherine Hamilton from NASA's Office of Communications. We are here at the Flight Robotics Laboratory flat floor at Marshall Space Flight Center to provide you an exciting update about the first launch of the Space Launch System rocket and the Orion spacecraft, and the science and technology that we'll be sending along to find out more about deep space. We will have two parts to today's program. First, we'll open with Marshall Center Director Todd May and NASA Deputy Administrator David Newman. Then I will announce the panel of representatives here on the stage to provide more details about today's announcement. In the second part of the program, we'll give you a behind-the-scenes look at some cool hardware that will be on that first flight with a mission of its own to learn more about an asteroid and test its solar sail technology. There will be a question and answer period at the end of each part of the program for media representatives present in the room, as well as those on the phone and following us on social media. For those joining us online, you can ask questions using the hashtag AskNASA. At the conclusion of the panel's remarks, I'll provide additional details about the question and answer period. And now, to start us off with a few words, Center Director Todd May.
Hey, thank you. It's good to have you all here today, and good to see all the folks that want to learn about the capability that we're bringing to the agency. Thank you for joining us today. This is a briefing to announce secondary payloads for the first launch of the Space Launch System, the largest and most powerful rocket ever built. You're about to learn about exciting capabilities of SLS above and beyond its primary mission. And that primary mission is to launch the Orion spacecraft into space beyond the Moon and onto Mars. It's the only rocket and spacecraft equipped to send humans and supplies required for deep space exploration. The first mission will be called Exploration Mission Number 1, and it'll be a proving ground mission, whose goal is to demonstrate the integrated performance of the SLS and Orion before we put crews on it for the first crewed flight. Because of the robust capability of the Space Launch System, we have a unique opportunity to transport small spacecraft and technology experiments on board the very same mission. Today you're going to hear about 13 small satellites that we're going to send out into space on this mission with the extra capability we have beyond that needed to launch Orion beyond the Moon. Here at Marshall, we manage the Space Launch System program, and we're tasked with integrating these payloads into the vehicle for the agency. We're also privileged to have two of the principal investigators, the Lunar Flashlight and the Near-Earth Asteroid Scout mission, and to manage one of those missions here at the center. All of the data from these missions and these experiments will be used to help us on our journey to Mars. And now I'd like to introduce you to Dr. David Newman, our Deputy Administrator, and someone who is very familiar with innovation and technology in her own right. She's in Washington, D.C., and she will tell you more about the importance of transporting these small satellites on the SLS and how the S&T, the science and technology gleaned from these missions, will advance us on our journey to Mars. Please help me in welcoming Dr. David Newman.
Thank you. Morning, everyone. And first, my honor and congratulations to Director Todd May, Marshall Space Flight Center's 13th director. Todd, throughout your entire career, you have consistently and persistently helped us advance exploration. So we're so proud of you and really look forward to working with you in this new role as director. It's great to be here in Rocket City. I love coming back to Huntsville. Today, get to highlight another step on our journey to Mars and our continued progress toward that first flight of SLS, the Space Launch System. In our journey to Mars, there are many facets, and it's really important to note that this Team Marshall is right at the core. We say it goes through, the path to Mars goes right through Huntsville and right through Marshall. So it's amazing work on the development and testing of SLS. And this first mission, as we know, is going to be about a little bit more than propulsion. It's also going to be about what science, what technology can we do, and that's why we're all here today for this very exciting announcement. Cubesats. Cubesats, 6 units, like a shoebox. They're really at the cutting edge of technology. They used to just be a dream. Today they're developed, and they're efficient, they're cost-effective. They're really showing us how to do exploration in a new way. During Exploration Mission 1, EM1 as we call it, NASA will expand our science and exploration capabilities by sending 13 of these small CubeSat-class payloads into orbit. And the design and advanced technology that we'll be flying is really setting the stage for our future human exploration missions. These 13 CubeSats that will fly, they're called secondary payloads, and they're going to showcase, they're really at the intersection. I like to think of it as being the synergy of what we can do scientifically and technology. So this is where it's a really good look of how much science and technology we can cram into that very small package, and you're going to be amazed when you hear all the details coming up. But it really is helping us advance our journey. SLS and their Orion spacecraft, they're going to take people further than we've ever taken people in human history. Further than we've ever been in over 4 decades, out into deep space and onward to Mars. So these technology missions in deep space are really something to pause, reflect on. We're not just talking about it, we're doing it, and it's starting right here. SLS is designed, and it has a flexible and evolvable architecture that's really important. The crew and cargo missions, they enable very large science experiments, technology demonstrations for exploring the universe, so thinking way, way out, and also they carry smaller secondary payloads and capabilities so we can test things out on these CubeSats. So as an aerospace engineer myself, that's really important. In systems engineering, thinking about the flexibility, how can we carry all kinds of different payloads from small to large, all kinds of science, all kinds of technology. That's really a new way to look at evolvable, flexible space systems. That's really what SLS demonstrates. EM1, Exploration Mission 1, is a proving ground mission, as Todd mentioned. What does that mean? Well, we're going out to deep space. This orbit leaves Earth, it goes to lunar orbit, past lunar orbit. The view from there is pretty spectacular when we look back on our own spaceship Earth. So these CubeSats that were chosen have the ability, and they really have amazing capabilities on board. You're going to hear more about the key information, and it really increases effectiveness and improves the design of subsequent robotic and human missions. So these are precursors, but they do their own science in their own right. And perhaps one of the most exciting things to me is what's going to be called the NASA's Cube Quest Challenge. Those ones haven't flown yet because the innovators are still working on them today. They're going to help test out spacecraft propulsion and communication techniques. So they're still in competition, working on those. So we'll just keep rolling out these great announcements. So that's a really amazing challenge that you're going to hear more about. So this is a very exciting opportunity. It's an incredible announcement. I'm so glad to be here in person with everyone. I look forward to the continued progress of SLS and the wonderful news like today's, which is helping us really bring to life, make it tangible, to celebrate the developments of exploration and to highlight the future missions that are happening here today at the Marshall Space Flight Center. Thank you all.
Thank you, Dr. Newman. Joining us here on the stage today to talk with us more about our deep space exploration journey and exciting science and technology along for the ride are Mr. Bill Hill, Deputy Associate Administrator for Exploration Systems Development at NASA Headquarters, Mr. Michael Sieblum, Chief Technologist for the Science Mission Directorate at NASA Headquarters, Mr. Jim Cockrell, CubeQuest Program Administrator at Ames Research Center, and Dr. Jitendra Joshi, Technology Integration Lead for the Advanced Exploration Systems Division at NASA Headquarters. At this time, we'll begin with our first panel member, Mr. Bill Hill.
Good morning, and thanks for being here with us to celebrate this great endeavor we're about to get on, the journey to Mars. This is going to be part of it, our CubeSats. Exploration Systems Development is making great progress toward our first test flight in 2018, the Exploration Mission 1. The Space Launch System, Orion, and the ground systems that support both pre-launch and recovery are making great progress. In 2015, we saw the completion of seven planned engine tests at Stennis. We saw a solid rocket booster test that was very successful. We have another one this year coming up in May. We got the Vertical Assembly Center at MAF, the largest single weld tool in the universe, up and running and working, and we're making great progress on our confidence welds as well as soon to be welding the Exploration Mission 1 hardware. We also saw the completion of the Orion pressure vessel, and we saw that delivered from MAF to KSC yesterday, and we'll begin very soon outfitting that. But today we're here to talk about the Cubesats that we're planning to fly and deploy on EM1. As Dr. Newman said, these are secondary payloads. Our primary mission, obviously, is the flight test, integrated flight test of Orion and the Space Launch System, as well as the ground systems that support pre-launch and recovery. We have selected 13 Cubesats for this mission. We could select up to 17. We've got those positions. We started with 11 and decided we had sufficient resources to do 13. Working both within NASA and with our international partners, as well as we made offers to the intelligence community, and because of our trajectory toward the moon, they declined that offer. Exploration Systems Development, internal to my organization, conducted a feasibility study of all the candidates, and we had more than 13 proposed, looking at the mission profile, and they down-selected to these 13, presented them to me for approval, which I did, and then we took them to our agency flight planning board recently and had them approved for flight. 10 of the Cubesats were selected from in-house through competitive processes, such as the CubeQuest challenge and the Next Step broad area announcement. 3 are international Cubesats that we're looking at and in negotiations today to get those on board. We won't be talking about those today. We'll find a future occasion to celebrate those and announce those. But each of these Cubesats are complementary to our objectives for human exploration and objectives for EM1, kind of at a smaller level. And they, as Dr. Newman said, press technology and science and provide us a capability that we might not otherwise have. Exploration drives science, and science drives exploration and technology. So with that, I'm going to pass it on to Jim.
Hi. Science Mission Directorate is really excited to be part of this opportunity to fly Cubesats on the SLS. Today's Cubesats represent a culmination of over 10 years of development, mostly by the academic community. The early missions that occurred back in the 2004-2005 timeframe were largely for educational purposes, and when there was a science payload, they tended to be somewhat pedestrian in nature. Today we have a convergence of the technology for miniaturization of instruments and also advancements in platform capabilities that have come together that have really enabled us to have a new science platform. Cubesats and other types of small satellites offer new opportunities for researchers to place their instruments in space, and we're not talking about investigators just at the large, more familiar institutions. We're really talking about new investigators from universities that have never before done business with NASA. We're seeing this now in our most recent solicitations. So it's great to see a very young and diverse set of researchers involved. It really does inspire the next generation. So in the Science Mission Directorate, we plan to continue to invest in technologies for miniaturization of science instruments through our dozen or so technology programs. And also, we will encourage the collection of scientific data from these observing platforms through our research solicitations. So today, I just wanted to introduce two of the two science payloads that will fly on the SLS. The first is the Lunar Hydrogen Mapper, or Luna HMAP, and the other is the Cubesat mission for science for investigating solar particles. The first mission is Luna HMAP. There's an image of it now on your screen. If we could go back to the first image, please. That's it. So you can see that this is the entire spacecraft. This is Luna HMAP, the size of a shoebox, with the rather photogenic PI. That's Craig Hardgrove. The purpose of the mission is to characterize the distribution of hydrogen that exists in the permanent shadows of the south pole of the moon, in the craters and on the plains. Because of the investments we've made in technology, this mission, which will carry a neutron spectrometer and also an imager, will give us unprecedented horizontal resolution of the distribution of hydrogen. Roughly 7.5 kilometers per pixel is what we're expecting. And if you could go to the next chart, you'll see the planned orbits in the red. There's an advanced propulsion system that has a dozen or so miniature thrusters to provide attitude control. This will give us more than 140 orbits over its planned 60-day life cycle. There'll be a Vertex 5 field programmable gate array processor for the science data processing, and they're going to be using JPL's Iris X-band radio for downlink communications. So it really is a convergence of a lot of technologies. The neutron spectrometer was miniaturized, and these platform technologies to provide the communications and the thermal control, all of these things have come together to give us a very cost-effective science mission. Okay. The next mission on the next chart is CUSP. This is also a 6U CubeSat, so 2 is roughly the size of a shoebox. CUSP will study this is a heliophysics mission. This will study the characteristics of solar and interplanetary particles, and will also contribute to our knowledge of space weather forecasting by examining superthermal particles and to better understand their role in contributing to geomagnetic storms. This mission contains 3 instruments: the superthermal ion spectrograph and the miniaturized electron-proton telescope. These 2 instruments will characterize the energy levels of these particles at different portions of the energy spectrum, and also a vector helium magnetometer to help characterize the magnetic fields. So both of these are highly cost-effective scientific missions that are enabled by our investments in technology and also by the contributions from our academic community. Thank you.
Good morning. I have the privilege of administering the CubeQuest Challenge. CubeQuest Challenge is STMD Centennial Challenge Program's first ever in-space competition for prizes. The contest is open to any non-government U.S.-based team that chooses to enter at no cost. The teams will compete through a series of events on the ground that we call ground tournaments, and the team selected at Ground Tournament 4 will be offered a free ride on the EM1 launch. There are 3 slots that have been allocated to the CubeQuest Challenge. The 2 years of events that leading up to the launch are called ground tournaments. Coincidentally, Ground Tournament 2 registration deadline is this Friday, February 5th. During the ground tournaments, the teams are judged by a panel of judges for technical excellence and compliance with the challenge rules and requirements. There are 4 of these ground tournament events leading up to the down select for the 3 that will be chosen to launch. After launch, the fun doesn't end there. The CubeSats, once dispensed in a translunar injection trajectory, will go on to compete for in-space prizes. And this is the first ever in-space challenge offered by NASA. Those teams that elect to enter lunar orbit, if they successfully achieve lunar orbit, win a share of $1.5 million prize. Some teams, and if you go to the next slide, rather than going to lunar orbit, they can proceed on to a range from Earth of 4 million kilometers. Now that's more than 10 times the distance between the Earth and the Moon. We call this the deep space derby, going to 4 million kilometers, as opposed to getting into lunar orbit, which we call the lunar derby. Now, whether in the lunar derby or the deep space derby, from lunar orbit or from 4 million kilometers, the teams then proceed to compete for accomplishments in communications achievements and for longevity. The last CubeSat we hear from will also win a prize. There's a total of $5 million prizes that will be awarded in the CubeQuest Challenge. And in order to win those prizes, our teams are going to have to demonstrate advancements in propulsion's capabilities, communications technology, and in order to navigate around the Moon or distances of 4 million kilometers, these little CubeSats that are briefcase-sized are going to have to advance their capabilities in autonomous operations and power management and navigation beyond the constraints of low Earth orbit. These are the kinds of capabilities that CubeSats are going to need as NASA proceeds on its journey to Mars. The capabilities that our teams are advancing, some teams are proposing doing laser communications from long distances. Other teams are advancing electric propulsion, perhaps solar sails, new kinds of electric propulsion, new kinds of chemical propulsion. These are the kinds of capabilities that CubeSats will need to be precursors for Mars missions in the future, or for exploration, man's exploration in deep space. And because by virtue of being small, lightweight, and made of affordable parts, we can accomplish NASA's future science and exploration missions more affordably with CubeSats. Currently, in the ground tournaments, we have 12 teams registered. 2/3 of those teams are from universities, 1/3 are from small businesses. In Ground Tournament 1, we even had one team that was a high school team. And one of our teams is a single individual retired engineer. So the competition is open to anyone who chooses to enter at no cost to the teams. Our CubeQuest Challenge teams we consider them citizen inventors, and we're excited to see how they're pushing the state-of-the-art of these small satellites. And we know that the teams are excited to contribute to NASA's exploration goals for science and for a future journey to Mars. And with that, I'll turn it over to Jitendra.
In order to enable future missions that are robust and sustainable, we need to have a good idea of what our destination looks like. To that end, we developed strategic knowledge gaps, which is more or less a repository of information that you need of your destinations based on what we know today. The next 5 CubeSats I'm going to talk about address these knowledge gaps that we need to find out more about. And let's go to the first one. So behind me you see a solar sail. This is half-size sail which will actually propel a CubeSat to an asteroid. This particular mission is called the Near Earth Asteroid Scout mission, which will go and do a reconnaissance mission with an asteroid about 100 meters in diameter. While it photographs it, we will get an understanding of what is the surface characterization, what is the morphology. Asteroids have a spin rate, which we need to understand. What is the dust or the debris that it emits out? All these things actually will help us design future human spacecrafts that will afford us a safe mission. So this acts as a precursor scout mission in order to understand and reduce our uncertainty in actually enabling a human mission. The next one, please. One of the biggest problems of deep space human missions that we would encounter is radiation. We haven't gone beyond the low Earth orbit in the last 40 years or more. This particular Cubesat mission, which is called a Biosentinel, and it will be an 18-month-long mission into deep space. It will carry with it genetically modified yeast, just like the baker's yeast you use. And with media, we will activate it periodically and see the effect of the radiation damage, both the solar particles and the galactic cosmic rays. This also carries a miniaturized sensor which not only tells you how much radiation you got hit by, but what kind of radiation. How does that help us? Understanding that radiation damage will help us develop preventive strategies for future human missions to enable safe human spaceflight. Next one, please. You see another lunar mission here, and let me just give you context. My colleague, Mr. Seablum, talked about a lunar mission. We also had various lunar missions before, the Lunar Reconnaissance Orbiter, the Chandrayaan mission with India, Selene mission with Japan. We had a Clementine mission before that. So one would naturally ask, why so many lunar missions? What are you trying to glean through? All those missions had instruments that help us understand the water or the hydroxide characterization. These CubeSats that I'm going to talk about, the one which Dr. Seablum and this one, this is called the lunar flashlight, which has actually lasers in a very narrow bandwidth. It will make several passes around the moon and look for volatiles and water species in the cold traps. It will give us a very good map of what the speciation of that water is, whether it is water, ice, whether it is water in a form that we can use. And how it helps us is in a future mission, we have to start living off the land where we go. So it helps us in mapping out sites for in situ resource utilization. Next one, please. We challenged industry and academia, and this was a new way of doing business for NASA through our Next Step broad agency announcement, where we challenged the partners, hey, you do your own internal research and development, and then we will take it with NASA in order to effect a mission. The mission you see here is Lockheed Martin's, through their own internal research and development activities, they developed a Cubesat which will do a lunar flyby and actually do thermography and surface characterization. After that one lunar flyby, it does maneuvers which will address some of the strategic knowledge gaps that are pertinent to an eventual Mars mission. Next one, please. This is a lunar flashlight. It also has, Mike talked of a neutron spectrometer. I earlier mentioned of laser spectroscopy. This has an infrared spectrometer which is very compact. It's called the Lunar Ice Cube, development activity with Goddard Space Flight, led by Morehead State University, BUSEC, and Goddard Space Flight Center. This particular infrared spectrometer will actually help delineate the water species, whether it's water, ice, and make several passes and make us help a composite map. So all these are complementary missions. The missions which we talked about earlier, which went to moon, were sizes of refrigerators. This is one of the compartments where you store vegetables in a refrigerator. So that's the kind of scale with almost a similar capability and delineating more information. Thank you.
We will now open the program for questions. I will rotate questions from those in the room and those on the phone, as well as those submitting questions online using the hashtag AskNASA. For those here on site, please raise your hand and someone with a mic will come to you. Please identify yourself by name and affiliation and indicate to whom your question is directed. And please ask only one question each to allow everyone the opportunity to get their questions answered. First question.
Hi, I'm Josh Barrett with Channel 31 here in Huntsville. My question for you, are you hoping to set a precedent with these 13 CubeSats on later exploration missions. So when they're going further out into asteroids, you could potentially even launch missions out towards those asteroids as well?
Well, I guess we could. These CubeSats don't weigh or don't have a great deal of mass, and we believe we've got sufficient capability to take them wherever we want. Limitations are, right now, we're putting these CubeSats on the Orion stage adapter, which interfaces between the interim cryopropulsion system and the Orion adapter or interface. So that's a nice, easy interface. That goes on a different trajectory than Orion will. We'll separate first and then deploy these CubeSats. We'll take a look at it. One of the great things about this opportunity with EM1 is we are, for the first time, going outside of low Earth orbit. We've deployed CubeSats from ISS and deployed CubeSats from expendable launch vehicles. This is the first time we're actually going beyond low Earth orbit and being able to deploy those. So we look forward to the future and potentially be able to do the same thing as we go further out.
Thank you. Next question. Over here.
Hi, I'm Lee Roop with AL.com here in Huntsville. Thanks for coming to Huntsville to do this. Just to kind of follow up on what Josh asked, if you did do these on future missions, is this something where young scientists can come up with their own ideas for what they would like to experiment on out in deep space, or is this something where future missions would have to, be related to strategic questions that NASA already has?
Well, I think I'll let my colleagues here talk to that as well, but I think the way we approach it, we give opportunities to almost anybody and come up with your own idea. We'll look at the compatibility with the mission, but I'll let you all, Mike.
So NASA actually does that already. We have something called the CubeSat Launch Initiative, where we look for space on spacecrafts that are going to different orbits, and high school students, universities, they develop CubeSats for that. What is different here is we have, over the last couple of years, developed capabilities for communications, for the transponders, the antennae, the gimbal arrays, the propulsion systems here. That is technology people can use now to go into deep space than just a low Earth orbit and a mission of months maybe. This will afford you years of observation.
So I'd just add to that, yes, we're calling all young folks, so the makers and the dreamers, think about your good ideas. It's perfect to start with this generation, and from high school or beyond, give us your good ideas, and we'll try to maximize all the payloads we can.
Next question.
Scott Johnson with the Spaceflight Insider. I know you have some models over here to one side of the stage. I was just wondering if someone could maybe reference those and explain a little bit more about the deployment of the CubeSats. I mean, what happens mechanically, that sort of thing.
We'll actually be talking about exactly that, in more detail in the second part of our program. Any other questions in the room here? All right, we'll conclude our question and answer session for now. We'll have a short video, and then we'll continue with the second part of our program.